Hello and welcome to the discussion sessions of this lecture series on production technology, theory and practice. Now, let me remind you that we started in our last session the discussion on the NC and the CNC machines, okay. And in particular we discussed the concept of adaptive control system. It was told that adaptive control system something that adapts some system which adapts itself to the environment. Okay. That means that suppose during the process, during the machining process, if the for some reason if the force is changing, okay, or if some other parameters are changing, then the adaptive control system will be able to correct those disturbances, eliminate those disturbances by manipulating feed or speed or both, okay, automatically. So, of course, these systems become more complicated, more expensive, because we have to have a series of sensors for sensing the signals, different signals. So, suppose you have the excess of vibration occurring, okay, excess of force occurring. In that case, the accelerometer, then force dynamometer, okay, and so on. So, you have to have some kind of sensors to sense what is happening and to find out that whether it is the extra force which is coming rather than what is given, what is desired or what is given as an input. Okay. Then it was told, if you see the slide, that adaptive controls are of two types. Okay. It was discussed in the last session that it can be either adaptive control optimization or it can be adaptive control constraint. So, in case of adaptive control optimization, an index of performance is specified for the system. Okay. Now, that index of performance should be a measure of overall process performance, such as production rate, okay, cost. The objective of the controller is to optimize the index of performance that has been selected by manipulating speed and or feed in the operation. Okay. In the second case, that is when it is adaptive control constraint, a constant level or constant limit is imposed on the measured processes, okay, or measured process variables. The objective of the adaptive controller is to manipulate speed and or feed to maintain the measured variables at or below their constant limit values. So, you can see that in both cases of adaptive control systems, the parameters which the adaptive control base on, that is the speed or feed or both of them, okay, that is the same, that is either speed or feed or both. And by manipulating the speed and or feed, the adaptive control system then adapts itself with the environment. Okay. And with the environment means when the parameters are changing. Okay. Now, then also we said that most adaptive control optimization systems try to maximize the ratio of work material removal rate to the tool wear rate. That means, the index of performance which is selected, this is convenient to have that MRR divided by TWR, because this reflects the reflects many of the aspects of the process, okay, because it is the material removal rate and the TWR ratio. So, material removal rate, for example, the production rate is reflected here, TWR, it is a tool life is reflected here, and so on. So, this is convenient that if we can optimize this index of performance, which is the ratio of the MRR and the TWR, then the adaptive control can be successfully operated. Let me give you an example of a typical adaptive control system. Okay. So, let us say we have the face milling cutter and this is the workpiece. Okay. Now, here what happens that this is the interrupted cutting, all right. in between we have some sort of air gap, all right. Now, here the system is in the following way, that there is a sensor. Okay. Now, this sensor senses the cutting force. Continuously the cutting force is measured, let us say this kind of a dynamometer, okay, which we have discussed. Now, the cutting force, while the milling cutter is removing material from the workpiece, cutting force is continuously measured here, all right. So, from here there will be an air gap detector. Okay. Air gap detector means that when the milling cutter will cut through the metal and then it will go through the air, it will not cut, and then again it will start cutting this other part where it is where the material removal is required. So, that air gap will be detected. How to detect the air gap? It is simple, because in that case the force becomes 0, all right. Now, in case the air gap is detected, okay, air gap is detected, then triple feed rate. In that case the command goes to increase the feed rate 3 times, all right. And if there is no air gap, in that case the metal has to be removed. So, therefore, adjust feed rate to maintain cutter force at the set value. Okay. Now, this is the cutter and here the force is being measured continuously. So, in case it has to go through the metal, in that case the feed rate has to be adjusted to maintain the cutter force at the set value, and we have a set value for the cutter force, let us say. Okay. Now, whether there is an air gap or there is no air gap, this is summed up, all right, and this value goes into the feed rate control. Suppose there is no air gap. Okay. So, in that case of course, cutting will be a normal, in the sense that there will be not much of an effect, because this force is already equal to the set value, all right. Now, this force will be reduced when there will be air gap. Okay. So, therefore, in case this happens, that there is an air gap and the tool goes through the air gap, then of course, feed rate is being triplicated. Then there is no signal from here, and this triplicated feed rate will go here and feed rate will be controlled, it will actually be implemented here. So, you can see that this is a closed loop, this is a closed loop control system, and this control system, this kind of a control system is called the adaptive control system. Okay. So, here you can see that there is a set value, and we are not optimizing the parameter as we have said here, index of performance. So, therefore, this kind of adaptive control system is called the adaptive control constraint, because the force value is set, and the force value, if it goes down or it goes up, in that case it has to be adjusted. For example, in this case there is no air gap, okay, it goes through the metal, but it may so happen that in between there will be the inhomogeneous in the hardness. Okay. Hardness is inhomogeneous. If the hardness is more and this is encountered by the tool, by the milling cutter here, in that case the feed has to be adjusted, okay, and the set value is here. So, it will always compare with the set value and the value which is coming from the measurement of the cutting force, okay, because there is no air gap. So, it will come through this. In case this is becoming more than the set value, then the feed has to be adjusted, the feed rate has to be adjusted, decreased. Okay. In case it goes through the air, so you do not have to, you can actually go it fast, because there is no cutting process. So, in that case you can increase the feed rate, and the feed rate can be increased 3 times. Okay. So, whatever is the result, it will actually come here, and to implement that whether the feed has to be increased or decreased, that will be done by the feed rate controller, and it will go as the implementation to the zone, machining zone, so that the feed rate can be increased or decreased, okay, to adjust the change in the cutting force. So, here the parameter, which is the disturbance, as I said that this is the external disturbance, let us say force is increasing or decreasing. So, this is the disturbance which is coming from outside. Now, the system, the adaptive control system, which is actually this circuit, this has to adapt itself. So, it will come as a signal and immediately it will tend to increase or decrease the feed. Mind it that this, from the time it is sensing and from the up to the time it is actually implementing, the difference is very less. Okay. Minimum is we have to try to minimize the difference in this time, all right. So, it has to be immediate, all right. So, this is called the lagging, that by the time the signal is implemented, some time has been elapsed. So, let me tell you, this can be within the time frame of 0.1 second. Okay. So, by the time it is sensed and up to the time it is implemented, the difference can be 0.1 second, not I mean this is a rough estimation of many of the adaptive constraint processes. Okay. This is the reality, all right. Now, benefits are manifold, like of course, the increased production rate, that is the online adjustments to allow for variations in the work geometry, material and tool wear provide the machine tool with the capability to achieve the highest MRR, and highest MRR means the high production rate. Okay. Increased tool life, because adjustment can be made in the feed rate to prevent the severe loading of the tool. Take example again, coming back to this, we are saying that here it is continuously being evaluated and the feed is adjusted. So, the tool is actually safe. Now, the not much of load is on the tool. I mean, there cannot be a sudden load coming to the tool, so that the tool life could be decreased, okay, or tool can be broken, because there are always the feedback system which is working, sensing the forces, and the feed is being adjusted constantly. Now, greater part protection, force limits can be established on the basis of work size tolerance. Okay. What will be the limit in the force? That depends on the work size tolerance. Okay. If the tolerance is very close, the force limit will be accordingly maintained. Less operators in intervention, because if you see in this diagram, there is no operator is required in fact, because here it is the sensor installed and sensing, all right, and the implementation signal is given here. So, there will be no human being and the involvement of the human being is not necessary. Easier part programming, selection of feed is left to the controller unit rather than to the part programmer. See, what happens is, that means that how much feed has to be given, either it will be increased, how much it has to be increased, or it has to be decreased, how much it will be decreased. Operator does not have to think about it, or the programmer does not have to think about it. You do not have to make that adjustment in the program, because program has nothing to do. This is the instantaneous, this is a dynamic process. Okay. It can change during the process any time. Okay. It can increase or it can decrease any time. So, it is a dynamic process, and the programmer cannot even guess, okay, cannot predict. So, therefore, the task of the programmer is easier, because all these adjustments, all these calculations and the decision that how much feed has to be adjusted, this is done by the adaptive control system itself and not by the programmer. Okay. Basic functions of the adaptive control system are these three, all right: identification function, decision function, and the modification function. So, you can see that these are the functions which actually normal human being does day to day, all right, that we identify something, that what to do, then we decide, okay, that how to do that, and then we modify that whether what you have done is correctly done or not. Okay. So, let us see here how the adaptive control functions. Identification function concerned with the determining current value of the process performance measured by making use of the feedback data from the process. Current value, what is the current status? Okay, coming back to this here. So, this is actually this is determining the status of the process. that whether the cutting force is within that set value, or it is fluctuating, it is becoming more or it is becoming less. So, instantaneously it will actually send the signal that what is the current status of the process, okay, what the process is going through. All right. Now, next is the decision function, to decide how the control mechanism should be adjusted to improve the process performance by means of a programmed logic. So, here this is suppose here this value of the force is equal to the adjusted value. So, the entire thing is silent, entire circuit is silent, because there is nothing to be done, feed does not have to be adjusted, because this value of the force measured is equal to the set value. Now, the moment it will actually increase or decrease, then of course, it will be activated. All right. In that case, what we are saying is that this will be decided, that what to do and how to do that, to decide how the control mechanism should be adjusted. Okay. It has to be increased, it has to be decreased, or what, to improve the process performance. All right. And that will be done by the programmed logic, and the programmed logic is all here. Okay. Here is this the programmed logic, the main function, that it will actually calculate that what is the discrepancy between the current value and the set value, and then it will decide that what has to be done with the feed, it has to be increased or it has to be decreased, and then accordingly it will be implemented. Okay. That is exactly what is said here. And the third function is the modification function, and the modification function is to implement the decision, physical or mechanical change in the system, changing the system parameters or variables. Okay. So, then finally, it will actually modify that, if whether it has to it has been done properly or not. So, basic three functions of the adaptive control system, which is very similar to what human being also does it. Okay. That is, our brain does it, that is identify, decide and modify. Okay. So, here you can see the general configuration of an adaptive control system. In the in the block diagram I have tried to show it. Now, this is the process. Okay. Now, in this process we have some process input and we are getting some output. All right. Now, from here on this process there are some time varying environment, and time varying environment we mean to say that there are certain kind of a disturbance, change in the force, change in the temperature, change in the vibration, okay, or created vibration created. Now, here from this input, output and the disturbance, these are the signals which will be continuously measured. This is the measurement. So, the measurement is done for the input parameters to the process as well as to the output parameters. Okay. So, input and output parameters, they will also vary, I mean output parameters particularly will vary depending on the time varying environment, because time varying environment will change the input. All right, you understand that it will actually change the process performance, and it can change this input. So, overall that will be detected when both these signals will be measured continuously. This here it identifies that whether it is correct or whether there is a discrepancy between the output and the input, and the discrepancy is only because of the time varying environment, you understand that. So, as soon as it identifies that there is a discrepancy, then it sends it to the logic circuit that you decide this is the discrepancy, now what to do. Okay. Now, the decision is made that you see feed has to be increased, or speed or feed, we said that these are the two things that the adaptive control system actually change. All right. So, the adaptive control system then decides that the feed or speed has to be changed, and then it sends this signal or decision to the modification function, and the modification function actually sends the voltage signal to the controller, so that the feed or speed whatever has been decided can be changed, and here we will have the system input. This is the entire system. So, the system input we will have some signal that will go through the controller, and the controller can say that you change this system, you multiply that with some coefficient, and that coefficient is decided here based on the identified values of the output and the input, whether there is any discrepancy or not, and accordingly it will go as a process input and the process will be changed. So, once again it will be done instantaneously, okay, and almost with the time lag of, as I said, that 0.1 second or even less than that. All right. Okay. Now, let me give you an example of the control systems and show you that how the adaptive control system can be helpful in establishing or in controlling the output parameter. Okay. Whereas, many of the NC systems, many of the closed loop systems, even that we have discussed in the numerically controlled machines, I mean earlier, that they are also not capable of doing that. All right. Let us take an example. Suppose we have a system where the transfer function is 5. Okay. Let the desired value of the output will be y. Let us say we have a process like this. Okay. Some process which is described as y is equal to 5 xp. Okay. Xp is the input, some input. All right. It may be in terms of voltage, in terms of some value. Okay. So, this will go through the black box here and it will be multiplied by 5. So, this is the gain of the process, it is called the gain of the process. So, at the output it will be equal to 5 into xp, the xp is the input. Okay. So, therefore, we said that this is called the transfer function. Transfer function is y by xp, this is the output by input, this is equal to 5, this is the gain of the process. Okay. Gain of the process is nothing but just imagine an amplifier. Okay. So, you increase that level decibel, okay, 5, 10, 15. So, you are increasing the gain, we say. So, this is the gain, that means this is kind of an, in case of amplifier it is the amplification factor. Okay. So, here also we are amplifying as if the input value by 5 and giving it to the output as y is equal to 5 xp, which is the equation or how the process can be described. So, therefore, the transfer function is 5, that is output by input, and let us say that the desired value, we want the output to be some 20 unit, some 20 unit. Therefore, the value of the input should be 5 into 4 20, okay, or 20 by 5 is 4. So, this xp has to be equal to 4. Now, we will make a feedback controller. Control the process, we have to have a controller, all right, and let us say the process gain is always 5, we are not changing that, and xp is the input and y is the output. Okay. So, this is the process, here it is the process, and to the process we are adding a controller and then we are adding a feedback system. This is the feedback control. All right. Now, as I said that the feedback control, with the feedback control there will be a sensor, it will continuously measure the output and it will actually go through some kind of an amplification, it will come to the input and the input value will be summed up with the measured value and it will create an error signal. Error signal means it will create a signal so that to compensate for the error whatever is coming. Okay. This error signal will go through the controller and then it will come as an input to the process. This input to the process, this can be changed accordingly, okay, depending on the measured value here. Okay. This is the feedback control system. Now, let us say the error signal, this is equal to this x minus this is by the way, this is actually the negative feedback control system. This is called the negative feedback. Okay. Negative feedback is mostly used because input is considered to be the plus on which the output signal is superimposed. So, this is minus, all right. So, therefore, the error signal is this input signal minus this signal, or this signal will be y into 0.1. Okay. So, 0.1 y. Now, x is equal to 4, there has to be 4 minus 0.1 y. Now, the xp next, this will be 2 into this, 2 into e, and 2 into e means y will be, we will come to that. Then y output will be 5 into this xp, xp is the 2e. Okay. So, therefore, the y overall, this will be equal to 5 into 2e, xp is 2e, and e is equal to 4 minus 0.1 y, you will put it. So, therefore, y will become equal to 20. Okay. See, the now this process is established process, or process is in equilibrium, where we wanted some output which is 20 and we are giving the input as 4, and then everything will be fine going on. Okay. Now, suppose the process is disturbed. Okay. Say, let us say for some reason, we are not discussing what can be, reason can be many, okay, and we are saying that for some reason the process is disturbed and the output has been changed from 20 to some value, let us say 25. Okay. So, now suppose the process is disturbed, throwing the output y this to a new value of 25. Okay. Now, if y is equal to 25, then we go to the in the reverse way. So, e, this error signal will be 4 minus 0.1 y, and y is 25. So, it will be 1.5. So, y is equal to 15 again coming here. Okay. Y is equal to 5 into 2e. So, you see, this is something, if we, meaning that if we have such kind of a process, okay, you can see here there is no contradiction. Okay. Let us say y is equal to 25, then error signal from this point of view is 25 minus 0.1, okay, and this will be added to the 4, or 4 minus this. So, this will be 1.5. Okay. Now, therefore, from here you can find out that y is becoming, which is 5 into 2e, and the error signal is 1.5. So, it will be 15. All right. That means, with this control system, this type of feedback control system if we have, and if the y becomes 25, then after a time lag of, as I said, for example 0.1 second after the measurement, after it comes back through the controller, the error signal and so on, it becomes 15. Okay. Meaning that such kind of a feedback control system is not capable of controlling the process and not capable of controlling the output, keeping the output at as a desired level, because we wanted the output to be at 20 all the time, whatever happens, isn't it? That is what we decided. So, suppose if the disturbance happens and this becomes 25, so the task of the system should be that it has to bring back to the system with the output of 20, which is the desired value. Okay. So, for a high value of y, when it is becoming higher, the error e will be low, isn't it? That we can see, because we have taken its amplification here as 0.1, reducing the y value, because y has become from 25 to 15. So, it is less than 20. All right. Similarly, if the low value will be there, let us say it has gone from 20 to 15, then it will increase, right. Y will tend to be increased by the system in the reverse way. All right. So, therefore, this system is not capable. That is the decision, that the feedback control system we cannot use to stabilize the system output. Okay. Now, with adaptive control system, with this control strategy, the adaptive controller will try to monitor the performance and compensate for the changes in the environment. Okay. Suppose due to change in the environment, a gain has decreased from 5 to 4. Let us say the next example we will see that in that process, because of some disturbance from outside, okay, this process gain has been changed from 5 to, let us say, 4. Then what happens? Let us see. Then how the feedback control system will behave. Feedback control will not be able to maintain the value y is equal to 20. Why? Let us see. E then will be x minus 0.1 y, okay, keeping that, and here we have the 4 minus x, x has become 4, x is 4 minus 0.1 this. So, this will be the same. Now, y is equal to 4 x p, right. Now, it has become 4 instead of 5. Y is equal to 4 x p. So, therefore, y value which is 4 into 2e, 2e is 2 into this, okay, will be here, and then y value calculated will be 17.777. So, similarly, as we have calculated here, the same thing we are doing it here. That only thing is here the process gain has changed from 5 to 4, and accordingly we are changing the process here. So, y is equal to then 17.77, which is not 20, it could not establish. Okay. Now, let us see with adaptive control. Here if you see in this, now let us say the index of performance we will select, and index of performance we will select as z, which is 20 minus y square. So, this is, as you know, this is called the least square error objective function. Okay. 20 is the desired value, this is the y which is output. So, 20 minus y square, this is the index of performance, and then our task as the adaptive control system will be to minimize this z. Okay. Now, we have three functions, we have identification function, we have then the implementation and the decision, okay, decision and the modification, these are the three functions. So, then what we do is identification function is the simultaneous measurement of x p and y. Okay. So, we will measure x p and y like we have given in this example, that input and output both will be measured simultaneously. Okay. And then the feedback control system will attempt to determine the mathematical function as part of its logic function, y is equal to k into x p. Okay. You understand what we are talking about, that y is equal to k, let us say some process gain into x p. See, what we are saying is this process we are taking as the dynamic process. So, any time it changes, k value will change. So, let us say this is in general we are writing that this is the logic function as y is equal to k into x p. Using the measured values of x p and the y, okay, we can find out the value of the k for any instance when the x p or y may change. You understand what I am saying? Okay. For any instance, k can be found out by continuously measuring y and x p, and continuously measurement is what we are doing. So, here in this example, as I said, that we are measuring this continuously. So, here also x p and y we will continuously measure, and we will find out the value of the process gain at any point of time when the x p and the y may change to some other values. Suppose the x p is 4, okay, for any instance, and y is equal to 16, then k is equal to, for that these particular values it is 4, but x p can have 4.1, y may have 16.2. So, accordingly you will find the k for the next instance of time. Okay. You understand what I am saying, that this is the dynamic process where x p and y may change, and whenever it changes, and if it changes, then the value of the process gain can be calculated, because we have taken already the equation. Now, I am showing it in a very simple example. You understand that any process can be in a similar way analyzed, and the process can be very complicated. So, this kind of equation will be very complicated equation, but the decision making logic instrument in the adaptive control system will be capable of calculating instantaneously that what will be the value of the k if the y output and the input x p change. Now, suppose for this particular values, when we are having k is equal to 4, the adaptive controller will then compute the value of x p to minimize the index of performance z. Okay, z is the decision function we have taken. So, z is equal to 20 minus y whole square, 20 minus y we have taken as the k into x, okay, or x p you have taken anyway. So, it is, let us say it is x and x p same. So, in that case it will be this value. Now, you take the minimize. So, it has to be first derivative equal to 0, So, if you take the first derivative, it will be this value. From here the k x is equal to 20, or x value is 20 minus 20 divided by k. Since k is equal to 4, x p will be 5. So, that means this is the conclusion, meaning that the modification then will be made in the process input, changing its value from 4 to new value of x 5, x p 5. Okay. So, if the process has become 4, then x p value will be changed to 5 instead of 4. So, this is the conclusion that the adaptive control will make, and then it will actually implement that way. All right. This is the entire process of the adaptive control system and how it can actually work. So, this is how it can actually happen, that output and input can be continuously measured. This is the identification function, okay, and this is the model which is formed. Find k, k is equal to y by x p. So, this will be decided, then x p is equal to 20 by k, then modification is changed the x p, and modification is given to the controller, controller sends the signal, and then it is changed, okay. The x p is changed to from 4 to 5 as we said. So, this is the block diagram saying the same thing that we have described in this adaptive control system process. That means, what has been told here in this analysis is that the simple feedback control system is not capable to stabilize the system when the when the system is disturbed by the output, by some outer disturbance. But adaptive control system will always be able to keep the output at a desired level. Let us say either it is then we have what we have said is adaptive control optimization. Okay. In this example, it is we have optimized the index of performance. So, we are minimizing this. Okay. So, therefore, it is the adaptive control optimization. However, adaptive control constraint can also be used, that I have already shown it to you in a block diagram. All right. Now, let us discuss what is the incremental and the absolute system. Incremental system is one in which the reference point to the next instruction is the end point of the preceding operation. An absolute system is one in which all moving comments are referred to one reference point, which is the origin and will be called as the 0 point. Why it is important? Because the manufacturer of the NC and the CNC machine will determine initially that whether it is going to be an incremental or absolute system. So, they can keep it both way. Now, in the program you have to tell that what you want, what is your drawing. So, what basically we mean that the incremental is, suppose we have a shaft. Okay. I will give a simple example, and this is these are the two different diameters a shaft has. So, the dimensions can be like this, right. Let us say this is A and this is B, or the dimension can be like this and this. These are the two methods. Okay. This is A and let us say this is C. So, either it can be given in this way, when it is all moving comments are referred to one reference point. This is the reference and this is the reference plane, or it can be reference point to the next instruction is the end point of the preceding operation. This is the preceding operation of this is the end point. So, from here next dimension will come. This is the only difference. So, we will see that in details in the later stage. Now, let me talk to you about the principle of the part programming, how the part programming can be done. Let me tell you that this part programming will be in very details shown to you in the lab, and I will also show it to you in a PPT before the lab session, that how the part programming can be done in an example. However, some of the points I would like to nevertheless tell in this lecture. Let us say a group of comments given to the CNC for operating the machine is called the program, first of all. Okay. So, the program will consist of 5 things, that is the information about the part geometry, motion statements to move the cutting tool, cutting speed, feed, and the auxiliary functions such as coolant on and off, spindle direction, rotation of direction of the spindle clockwise or anti-clockwise and so on. Okay. Now, program structure, there are 4 basic terms used in the CNC programming: character, word, block or and the program, entire program. All right. Now, fixed 0 versus the floating 0. Fixed 0 is the origin is always located at some position on the machine table, usually at southwest corner or lower left hand of the table, and all tool location are defined with respect to this 0. Okay, so, this is the fixed 0. Normally, it is set by the manufacturer. Okay, he can take it some point at the left side, okay, or southwest corner meaning that here somewhere at the left, because it is convenient, and then everything you can either give it with respect to this point, that all the other dimensions will come with respect to the fixed point, and the fixed point is here. Now, there is a floating 0 also. Floating 0 is very common with the CNC machine used nowadays, okay, the common, I mean the modern. Operator sets 0 point at any convenient position on machine table, meaning that it may not be convenient for me or you as an operator to operate your dimensions with respect to the fixed 0 that has been decided by the manufacturer. Okay. So, in the modern machines, what is done is there is a floating 0. So, wherever you would like to put your 0, that means the 0, what we mean by 0 is that all dimensions will be from there. I will show it to you later on. So, operator sets 0 point at any convenient position on the machine table. The coordinate system is known as work coordinate, okay, is as work coordinate system. So, this coordinate system, when you have the 0 point at any convenient position, this is in brief it in small this thing abbreviation, it is called the coordinate work coordinate system, WCS. Okay. Now, the modal and non-modal comments are the following, that is, comments issued in the NC program may stay in the effect indefinitely, okay, until they explicitly cancelled or changed by some other comment. Or they may be effective for only the one time that they are issued. Okay. I will explain it to you. Now, the former is referred to as a modal comment. So, this is the modal comment where it stays indefinitely until unless you change. Okay. Examples include feed rate selection and the coolant selection. Okay. Now, the comments that are effective only when issued and whose effects are lost for subsequent comments are referred to as a non-modal comments. Okay. Now, let me give you an example. Suppose you have selected in one program, in one line you have selected the feed, all right, certain value of the feed, let us say 0.1. Okay. Now, in the next line of the program you are not putting any feed, meaning that if it is the modal comment, that means the previously selected feed is still remaining remaining valid. Okay. Now, in the next line you are selecting again feed and giving the value as 0.2. So, once you are giving the value of 0.2, that means that 0.1 value which has been taken earlier, this is cancelled now. Okay. Now, in the non-modal comment, okay, you have to specify in the program whether it is a modal comment or it is a non-modal comment. In the non-modal comment, once you are giving the feed in one line, like in this case, in the next line also you have to repeat that. Okay. Otherwise, the comment will not be valid. In the next line, if you are not repeating that the f is remaining 0.1, in that case the f will be taken as 0 if nothing is written there. Okay. So, this is the non-modal comment. A dual comment which instructs the tool to remain in a given configuration for a given amount of time is an example of a non-modal comment. This is, I also gave you an example. So, anyway, this is the same thing. Now, the structure of an NC part program is made of a series of comments that are input into the MCU in a series manner. Okay. The MCU interprets these comments and generates the necessary signals. MCU is the machine control unit, okay, to each of the drive units of the machine to accomplish the required action. All right. Now, program is made, series of comments are given. As I said, those comments can be written in the alphabets A, B, C, D, in the M code, G code, okay. Miscellaneous is the M code, G code is the preparation, and so on. So, that I will show you each of these comments, and MCU will interpret them. NC program is required to have a particular structure that the controller can understand, and it must follow a specific syntax. Okay. That is the program, that is this G code, M code, etc. So, that the MCU can actually interpret, because it is already input in this MCU. Comments are inputs into the controller in units called blocks or statements. Each block is made up of one or more machine comments. I will show you those blocks. Many comments could be there, or a particular comment could be there, depending on what kind of machining, what kind of operation you are performing. Okay. In general, several comments are grouped together to accomplish a specific machining operation. Okay. Hence, the use of a block of information for each operation. All right. Each comment gives a specific element of control data, such as dimension or the feed rate. All right. Now, each comment within a block is also called a word. Now, we have a block, few comments, and each comment is a word. So, these are simple, this is not so important. I mean, you have to just write the program, that is what you have to be bothered about. The way in which the words are arranged within the block is called the block format. 3 different block formats are used: fixed sequential format, tab sequential format, word address format, and so on. So, those are the minute details. You may not require all those details during the programming, because when you are getting expert in programming, you actually do not really bother about those things, though they come automatically, I mean to say. Okay. Now, word sequential format used on virtually all modern controllers. For example, this is a program. Okay. Let us say, I will not explain what it is, but I will come later on, just an example that these are the 3 lines. Okay. With this type of format, each type of word is assigned as address, that is identified by a letter code within the part program. Okay. These are the letter code X, Y, F, G, N. Okay. Thus, the letter code specifies the type of word that follows, and then it associated numerical data. Let us say X is what to do, what is actually, and what is the value 50. For example, the code T represented tool. Okay, here the T is not given, suppose the T is given, and the tool number is given afterwards. So, T01 means the tool and tool number 1. Theoretically, with this approach, the words in a given block can be entered in any sequence, and the controller should be able to interpret them correctly. Okay. With the word address format only, the needed words for a given operation have to be included within the block, all right, and so on. So, word format has the advantage of having more than one particular comment in one block, okay, something that would be impossible in other 2 formats, and so on. So, these are the difference between the three formats and how they differ from each other. Okay. Now, commonly used word addresses, these are the N code, which is the number. Okay. Here N is 50, N is 60, N is 70. So, this is the number of this line. Okay. Each line is given by a number. N code, this is the sequence number. Okay. G code, this is a preparatory word. Preparatory word means used as a communication device to prepare the MCU, machine control unit. The G code indicates that a given control function, such as G01 for example, stands for linear interpolation. Okay. So, if it is given in the program that it is G01, G can be 01, 02, 03 and others. So, that will be tabulated. I mean to say, I will show you a table where all these codes are interpreted, all right, what is the interpretation of each of these codes. Now, G code, that is actually the preparatory word, it is given here as 01. 01 particularly means the linear interpolation. Okay. Now, x, y, z codes, these are the coordinates like in normal case. These are given, these are the given coordinates, okay, or the coordinate positions of the tool particularly. F code is the feed, S code is the spindle speed, T code is the tool selection, M code is the miscellaneous function, I, J and K they specify the center of an arc. Okay. And particularly it is when you are giving the circular interpolation, we will see that I, J and K codes are used, can also be used, or otherwise also it can be given as a circular interpolation. Okay. This is an example of whatever we said, that is the sequence of format and format. Let us say we have this, okay. This is as a program. Now, this is the sequence number 3, okay. G is the preparatory function, particularly the value here is the 2 means something. X and y, these are the destination coordinates, x y coordinate, z coordinate, all right. This is the distance to center of a circle, that means I and j. You remember we said I and j, these are the center of a circle. K is the feed rate, sorry, F is the feed, I, J, K will be the distance distance to center of circle. F is the feed rate, okay. S is the spindle speed, I am sorry this has been shifted here, S is the spindle speed actually, okay. This comes in here, okay. Tool is here, so this is the tool function will be here, okay, and M is the other functions miscellaneous. So, spindle speed is S, F is the feed rate, okay. F is the feed rate here. So, this is simply shifted and so on. Now, here these are the two tables, the one that I was telling you, that this is the table which shows the address words used in the NC A to Z. This is the number, sorry, this is the M, miscellaneous code. Miscellaneous code, you can see that there are many of them, and each of them has a meaning, okay. And of course, you do not have to remember all of them, and you cannot remember all of them, but when you will be practicing the programming, you will see that most of the normal miscellaneous comments you will be knowing automatically, okay, because you are using it very frequently. Otherwise, you will always have that table in front of you, and you can use that table to find out which comment to be given depending on your machining process, okay. So, for example, you know M01, this is optional program stop, okay. End of program, you want to say, you say M02, it will end. You want to spindle, you want to rotate the spindle in the clockwise direction, you write M03, okay. To the anti-clockwise direction, counterclockwise, it is M04. You want to switch it off, it will be M05. So, since there will be no intervention of the human being, everything should be done by the command given to the machine. So, these are the codes that has been coded in the machine, that machine should understand if it is given here, and this combination of all those will make a program. It is as simple as this, okay. And you will have these, each of them tabulated, you will be knowing them from the table, you do not have to remember them by heart. Similarly, the G code, you see there are 100 G codes, all right, and each G code, like in the M code, these are all tabulated and this have some meaning. For example, very popular is linear positioning, linear interpolation, circular interpolation, clockwise and the counterclockwise. These are very commonly used, okay. We will see that in programming. XY plane selection, ZX plane selection, okay, 17, 18, 19 they are also used. You have to put it in millimeters, so you have to make the program, make the machine to understand that whatever dimensions you are giving, these are in millimeter or in inch, because as you see here you will be given 1.4, you will not write here inch or centimeter or millimeter, okay. So, this command has to be given earlier in the program, that everything that is given in the program will be in millimeters. So, this is given by G21 and so on. You can see that there are many of those comments, and which each of these comments means something. Okay. So, depending on that, the whatever is the code and whatever is this value, okay, you have a particular meaning of that, and the combination of that, as I said, this is the program, nothing else. Okay. Let us see, like for example, this again the M code. M code is you have to stop the spindle, I told you, tool change will be M06 and so on so forth, coolant off, coolant on. Okay. Even whether you want to do the mist coolant or the flood coolant, that also should be given in the program, because again there is no intervention of human being. So, human being is not there, it cannot change the coolant from mist to flood or so on. Okay. It has to be given in program. And finally, these are the coordinates. So, I told you already that in case of turning lathe, the movement in this direction is considered to be x axis, and in this direction is the z axis. Okay. In case of drilling, this is z, this is x, this is y. In case of milling, this is z, okay, this is the horizontal milling, okay, and this is the z and this is the y. Okay. By the way, in case of vertical milling, this will be similar to this, okay, that is z, x and the y. All right. The rapid traverse, what is rapid traverse? This is given here, that there is a program for the rapid traverse, okay, and there is a code for the rapid traverse. That means, rapidly you have to move the tool from the 0 position to the actual position that you want near the workpiece. Okay. And linear interpolation, I have already explained to you what is linear interpolation. So, I am not really going into more details. Okay. These are the circular interpolation, that means either you can give it by the ijk, that means these are the coordinates, okay, or you can give it by the radius, as I said. So, circular interpolation means, I already told you earlier also that this has to rotate in a circular way, because you have to make a part of the curve, let us say sector of a curve. Absolute positioning I already explained, I am not going into more details, because from one base you are saying that, or you have to give it in a incremental. So, you have to say what is incremental, what is absolute. If it is absolute, the code is G90 and so on. So, in brief, what I want to say is that these are the comments, these are the easy comments which I can find out from the table, and accordingly you can make a program depending on what is the type of the machining that you are going to make. Okay. And examples I will give you in the lab, as well as during the before the lab, if we I will give you a PowerPoint presentation, and there also I will show you how a program is made in details. Okay. So, for example, just quickly I will go through that. Let us say we have a part to be made here. So, these details I will tell you in before the lab, as I said. Okay. So, here this is the 0 you decide, and the now all these dimensions which are given in the program will be given relative to this point. Okay. So, you can see that all these are given in this way, all right, and each of them has a meaning, as I said. Those details I will tell you in the laboratory. That is all what I wanted to tell you about the computer numerical program, and the details we will show you in the lab. I will show you specially the programming part in the before we go to the lab. Okay. So, that is all for this section. We will start in the next discussion session, we will start another topic which will be metrology. Thank you for your attention.